Good morning everyone and welcome to today's worked exam answer video. Today I'm having a look at a calculation question that comes from an AQA AS paper, could also appear in an AQA A-level paper, and within this calculation we're having a think about waters of crystallisation and using some experimental data to calculate a value for X, which is the number of moles of water of crystallisation within our hydrated compound. So the first thing that we are told in this question is that we are heating a solid sample of sodium carbonate .xH2O, which are the waters of crystallisation. We're doing that for a minute to remove water and determine a value for X. Figure 3 shows the apparatus used. So what we can then see here is by heating this little, I imagine it will be like a crucible or looks a bit more like an evaporating basin. Whatever it is, we're going to be heating this hydrated sodium carbonate. When we heat, the water of crystallisation will evaporate. Because it's got no lid, the water will escape, leaving us with only the anhydrous sodium carbonate or the non-hydrated version. We can therefore measure the masses of a few different things prior to and after the experiment and use those values to then, as it says, calculate a value for X in the formula Na2CO3.xH2O and give our answer to 2 decimal places. So what I wanted to do was colour code the 3 different components of this question. So we've got the solid that we start with, which is the sodium carbonate .xH2O, which I've been doing in the purpley colour. Then we're going to have the water that's removed, and I need to work out how much water has evaporated from the sample, which is going to be in blue. And I also need to therefore work out how much of the initial solid that's left over is the anhydrous sodium carbonate, and I'm going to do that in the orangey brown colours. So let's go back and have a look at what data we've been given in this table. So we've been given the mass of the empty evaporating basin, so just the evaporating basin itself, 24.35 grams. Then the mass of the evaporating basin and the solid before we heated it, which is going to be this solid here, that came to a mass of 25.47 grams. Now it's a bit sneaky that they've included the mass of the empty evaporating basin, because from these first 2 values we can calculate the mass of the Na2CO3.xH2O solid that we put in the evaporating basin to start with. But that's not actually going to be useful for us in the calculation that we're going to do. What we essentially want to do is do an empirical formula calculation, but rather than dealing with individual elements to figure out the ratio of those elements in a compound, we're going to be doing an empirical formula to get the ratio of the Na2CO3 to water. Now, based on this overall formula, the sodium carbonate .xH2O, we should get a ratio where the Na2CO3 solid is 1, and then the value of X should be it might be 1, they might be in a 1-to-1 ratio, but I would imagine it would be in a 1 to a bigger number than 1 ratio. And X should ideally be a whole number. Now it says give your answer to 2 decimal places here, because having done this question before, I know that X is not going to be a whole number. And in this case, that's because of errors that they've made in the method. So they only heated it for a minute, they didn't let it cool down, weigh it, then reheat it, let it cool, weigh it again. There's no heating to constant mass going on here, which is what we should always do with something like this, because how do we know after a minute that we've removed all the water? The answer to that is we don't, unless we then heat it again and the mass stays the same, and you would continue to heat it, let it cool and weigh it until the mass of what was left over in the evaporating basin stayed the same, and the latter part of this question did go on to talk about that. Therefore, our value for x is not going to be a whole number. So we've been asked to give our answer to 2 decimal places, whereas ideally, when we get to this ratio, it should be 1 to something. I think it might be 10 in this particular hydrated compound, but there's examples where it's 1 to 5, examples where it's 1 to 7, examples where it's 1 to 2. Depends on the nature of the kind of ionic compound you have initially. So the third piece of data that we've got is the mass of the evaporating basin and the solid after heating for 1 minute. So what we're assuming initially in this question is that heating it for 1 minute is enough to remove all of the water. So then the mass of the solid that's left over would just be the sodium carbonate minus all of the water. And then because we know that and the mass of the empty evaporating basin, we can then get the mass of the Na2CO3. If we know the mass of the evaporating basin and the solid before and after heating for a minute, we're assuming that all this mass that's been lost has come from the waters of crystallization evaporating. So we can then use these two numbers to figure out the mass of the water that has been driven off here. So the way that I'm going to set this up, I'm going to have my Na2CO3 as the anhydrous solid in one column, and I'm going to have the water in another column. And the first thing we need to work out from the experimental data is the mass of these two things. So this is where we've got to think really carefully about what data in the table we're going to use. So I think the water one is a bit more or a bit easier to see. So we've got the mass of the solid before we heat it, the mass of the solid after we heat it for a minute. The difference in those two numbers there is going to tell me how much water has been evaporated. So I am going to do for the water 25.47 take away 24.92, and that gives me 0.55 grams for the mass of water that we removed via evaporation. For the sodium carbonate, the anhydrous sodium carbonate, I need to use the mass of the evaporating basin and the solid after heating for a minute, because as I said, we're assuming that that value there represents all of the water having been evaporated, and we're going to need to know the mass of the empty evaporating basin to be able to figure that out. So although it can be confusing to have it and people might work out the initial mass of the hydrated sodium carbonate added, we do need it to be able to work out the mass of the anhydrous solid left at the end. So to work out the mass here, I'm therefore going to need to do 24.92 take away 24.35, and that gets me 0.57 grams. Now I guess another way that we should be able to do that is to work out the solid before we heated it, so to work out the mass of this Na2CO3, because conservation of mass tells us that we would need to then have the same total mass of the two products as we do the initial hydrated solid. So if we were to work out the mass of the solid before heating, so 25.47 take away 24.35, that comes out at 1.12, and these do add up to 1.12. Therefore, if you were struggling to figure out how to work out the mass of the anhydrous sodium carbonate, but you could work out the mass of the initial hydrated, you could do the 1.12 grams of this, take away the 0.55 grams of water, and figure out the sodium carbonate that way as well. So there are a few different ways we can do that, and it's obviously depends on what you find easier to work out using the data you've got. But these are the two masses that we need. Now in any empirical formula calculation, we are going to use the mass and it's usually the AR of the elements, but obviously we're going to use MR because these are compounds, so that we can then work out the moles. So the next thing that I need to do is work out the MR of these two compounds. So hydrogen each is 1, oxygen is 16, so the MR of water is 18. For the sodium carbonate, it's 23 for sodium, which we need twice, 12 for carbon, and then 3 lots of 16 for the oxygens, and that gives me an MR of 106. Now that I've got the mass and the MR, we want to be working out moles. So moles is mass divided by MR, so we're going to do 0.57 divided by 106 and 0.55 divided by 18. And for those answers, I get 5.38 times 10 to the minus 3 for the sodium carbonate, and then for the water 0.0306, to give them both to 3 significant figures. Then, as with any empirical formula calculation, it's figuring out the ratio between these moles. So I would shorten that to say the simplest mole ratio, which is what SMR means. And to work out the simplest mole ratio, it might be that you can just look at the numbers and go, we've got 0.25 and 0.5, so therefore the ratio is 1 to 2. These numbers, not very easy to see this at all. Now it should be that the moles of the anhydrous solid is smaller than the moles of the water, because we are going to divide both of these mole values by the smallest moles, which is this. So if I then do 5.38 times 10 to the minus 3 divided by itself, I'm going to get a value for 1, which we need to get so that we can then figure out the moles of the water as our X in that hydrated formula. So that will give me 1 for the sodium carbonate moles, and then I'm going to do 0.0306 for the moles of the water divided by 5.38 times 10 to the minus 3, and that will give me the value of X. Now when I do that, I get an answer of 5.68226 blah blah blah. I need to give it to 2 decimal places, so 5.68. Now, like I say, that would normally come out as a whole number or exceptionally close to a whole number, so you might get 9.97, 9.98 if it was meant to be 10. That tells me that this has not been a very good experiment, because 5.68 moles of water, X is normally a whole number. That is obviously clearly not a whole number. However, here, the clue that we know that it's okay to go with that is that when working out a value for X, we were told to give it to 2 decimal places. And as I've said, when this question then goes on, it would ask you why we didn't get the right value. I'm pretty sure it tells you that the value for X should be 10, and you have to consider why the value that you've just worked out is not 10. And that comes down to the lack of heating it to constant mass, as I discussed earlier. So that would be the calculation that you'd need to do. And for any question like this, where you're working out a value of X for the waters of crystallization in a hydrated compound, you would do the same thing. I think it's more difficult when you get presented with practical data like this than if you were just told this was the mass of the initial solid, this was the mass of the solid that was left over, and so on and so forth. But if you think carefully about what the data is telling you, I think it's not too bad to work out the masses, and then from there it's a normal empirical formula calculation: mass, MR, moles, get the simplest mole ratio, and whatever value you get when you divide the moles of the water by the moles of the anhydrous solid, that will be our value for X. As always, please let me know if anything that I have shared in this video is unclear. If you've got questions, you can leave them in the comments, or you can send me an email to missgtutoringandresources@outlook.com. Thanks so much for watching, guys, and I hope you have a really great day.